Okay, this honors chemistry lesson is on ionic radius. In order to talk about ionic radius, I'm going to review Coulombic attraction and the shielding effect, and then see how that relates to atomic radius, and then we'll go into the radius of ions. So you should have your sheet with you that looks just like mine, so you can take notes as I go. So let's start here at the top. Many properties of elements are based on electrostatic forces between positive and negative, and negative parts of the atom. So we're talking about protons and electrons. So those forces of attraction and repulsion, as well as the distance that separates these charges. So we're talking about distance, and then we're talking about the electrostatic forces. Okay, let me get rid of that. So these are called Coulombic attractions, and they're named after a scientist named Coulomb, and he came up with an equation that talks about the electrostatic force, so force electric, between two charges is related to the mass of those two charges. So let's say we have the mass of charge 1 and then the mass of charge 2. And that is inversely proportional to the distance squared in between them. Okay, so our two variables are the mass of the charges. So if we increase the mass of the charges, that's going to increase the force electric. And if we increase the distance, so if we have a bigger d, that's going to decrease the force electric between them. Okay, so that means the farther apart charges get, the less attraction they have, but the bigger the charges are, or the more charge that we have, the higher the force of attraction there's going to be. Okay, so you don't need to know this equation, but just so you know where it comes from. The force attraction between positive and negative charges is called Coulombic attractions. Factors that determine the strength of Coulombic attractions are, as I said, the distance between the charges. The greater the distance, the less attraction, and then the number of charges. So I said the mass of charges. So in chemistry, we're going to think about the number of charges as increasing the mass. So the more charge, the greater the total of the charge, the more attraction. So in an atom, this refers to the total charge of the nucleus. So that's the number of protons. Remember, protons are in the nucleus. And its attraction to the electrons, which are out here in the electron clouds. Okay, the shielding effect. The shielding effect is caused by the repulsion between internal electrons and valence electrons. Okay, so recall that valence electrons are the electrons in the highest energy level. So let's look at this depiction of an atom. This is considered a Bohr model because we see that the electrons are in these nice circular orbitals around the nucleus. In reality, it looks a little bit different. It looks more like a cloud, but for illustrative purposes, this works. So we have the valence electrons. There's two valence electrons in this model. So we have two here, and they're the outermost electrons. And then we have all these electrons here that are in between, or internal electrons. And effectively, they are shielding the attraction, the force of attraction between all the protons here in the middle and these two valence electrons on the outside. Okay, so the internal electrons, the electrons not in the highest energy level, or they're the ones that are closer to the nucleus, and the valence electrons are in the highest energy level. All right, let me move it down. Okay, so shielding the electrons that lie between the nucleus. All right, so we have the nucleus and the electrons in the highest energy level. Highest energy level, also known as the valence electrons, shield the outer electrons from the effect of nuclear charge. Thus, the attractive force felt by the valence electrons is less than the full positive charge of the nucleus, which means they have less attraction to the nucleus. So as you're going to learn in chemistry, these valence electrons are the easiest to be lost or the easiest to be gained, depending upon whether we have a cation or an anion. And these are the electrons, these valence electrons are the ones that are involved in bonding. So when something ionizes, for example, since this only has two valence electrons, these two electrons are going to be lost, okay? And so we would say then this ion has a +2 charge. Okay, so they are, one, the farthest from the nucleus, so that's the distance, okay? So they're going to have the least amount of attraction, and then they're also shielded by these internal electrons. Okay, so let's look at an example of sodium. So shielding in sodium results in the outer electrons experiencing an approximate pull the same as a single proton, because the 10 electrons between the nucleus and the outer electron block the charge of about 10 of the 11 protons. So let's look at this example. Here's our 1 valence electron. And then we have these 10 internal electrons, okay? So this electron here, this valence electron, is shielded from the pull of the positive nucleus, okay? So it's easily lost. That's why sodium, when it ionizes, makes it Na+1. It loses its negative charge, and then it'll have one more positive charge than negative. Okay, let's look at an example of a an anion. So shielding in chlorine results in the outer electrons experiencing a pull of approximately the same as 7 protons, because there are still only 10 internal electrons blocking the charge of the nucleus. Therefore, the outer electrons feel a greater attraction to the nucleus compared to sodium. Okay, so here we have 1, 2, 3, 4, 5, 6, 7 valence electrons. Okay, and so that means that electrons are always repelling one another as well. Okay, and so they're repelling one another and kind of spreading out as far as they can from each other, while at the same time being drawn towards the nucleus from the 17 protons, the attraction to the 17 protons. So they're being pulled in a little bit more because there's 7 of them here. There's quite a few, and the distance between the nucleus and the valence shell has not increased as we've added electrons. So the easiest way to see this is when we look at the actual atomic radius. So we see how shielding affects the atomic radius of different atoms. So here's the trends in atomic radius. As you go across the periodic table, what do we see? Well, from lithium all the way down, this is period 2 on the periodic table, to neon, we see that they're getting smaller. And that's because we're not adding any new energy levels. Our valence electrons are all being added to the same energy level, and that they're just being drawn in closer. So those positive negative attractions with the nucleus are drawing in the electrons closer, okay? However, if we go down the periodic table, we're adding a new energy level every time. And so our valence electrons are getting farther and farther away from the nucleus, and so the radius of the atom is getting larger. Okay, so we can say this formally. As we go across the periodic table, positive charge increases, but the distance to the electron stays the same, so the electrons are drawn in closer. So that's going across. And then going down the periodic table, the increase in the number of occupied orbitals, so energy levels, shields electrons in the highest energy level from the attraction of the positive charges in the nucleus, so it gets bigger. Okay, so let's just review atomic radius quickly. If you should have already done this, but if not, atomic radius, formally defined as half the distance between the 2 nuclei of atoms of the same element chemically bonded together. Now, this doesn't happen for all elements, but that's just how we're going to define it. It's most common for gases like chlorine, fluorine, oxygen, or there's a mnemonic for remembering the diatomic elements that you'll learn, Hofbrinkel, but chlorine is one of those atoms that's always found diatomic, meaning it's Cl2. Okay, so in the Cl2 molecule, the atomic radius of chlorine is half the distance between the nuclei of bonded chlorine atoms, so that equals 198 picometers. Picometers is times 10 to the negative 12th. Not that you need to remember any numbers or anything, but just remember that that's what the atomic radius is defined as. Okay, and as we saw in the graphic above, going down a group, the radius increases. That's because we're adding energy levels. More primary energy levels, valence electrons are farther from the nucleus, thus less attraction and a greater radius. The other reason is increased shielding. Increased shielding as we move down the group means that the nuclear charge felt by atoms in the same family is approximately equal. So remember, families go up and down. They're the columns on the periodic table. All right, and then thinking about going across. So let's go from left to right. So going across a period, those are the rows. From left to right, atomic radius decreases. And because of that, shielding does not increase across the periodic table, but nuclear charge does. We're not adding any energy levels. Thus, the net pull felt by the electrons is greater, and they are drawn closer to the nucleus. The number of energy levels is constant, therefore, it is not the major factor in determining this trend. So distance is not the major factor. All right, now getting into ionic radius. We have to remember there's two types of ions, cations and anions. All right, ionic radius is the radius of positive or negative ions in an element. Okay, so positive ions are cations and negative ions are anions. That's how we say that, cations and anions. So let's look at an example of sodium, which I have over here again. All right, the radius of sodium is about half the radius of the sodium atom. Okay, well, why is that? When a sodium atom loses an electron, the attraction between the remaining electrons in the nucleus is greater. Okay, this draws the electrons closer to the nucleus and it results in a cation being smaller than the atom. All right, so that's your trend that you need to remember. So let's think about this. So this is sodium, and when sodium becomes a positive cation, this goes away. All right, and what we're left with, we kind of lose this whole energy level, and what we're left with is essentially still 11 protons, and we have one less negative charge, so that's going to pull these electrons in closer. Okay, so the Na plus 1 is going to be smaller than the Na atom. All right, well, what about anions? It's a little different. Let's do chlorine again. So the radius of chlorine ion is much larger than the atom. As the number of electrons increases, the attraction of the nucleus for one electron decreases. Thus, the greater number of negative charges repel one another, and the size of the anion increases and is larger than the atom. All right, so over here we have 1, 2, 3, 4, 5, 6, 7 valence electrons. And what happens to chlorine when it becomes an ion? Well, it gains an electron. All right, so here we're going to make 8 electrons, the 8th electron. Now it has one more negative charge than it did before. And these things are going to, the electrons are going to repel one another, and that's going to make it larger than just chlorine, the chlorine atom. Okay, so our trends are then, anions are larger, and cations are smaller. Now I'd like for you all to complete the practice that comes in this packet, and then in the next video I'll go over the answers.